Good morning, everyone. Okay, there were a few questions that were asked to me outside, which are not directly related to what was done yesterday. So I thought I'll bring it up to you guys. One of the questions that was raised was, how does R2 change? Meaning that R2 is the transverse relaxation rate that's related to 1 over T2, right? So the question was, how does this value change? Basically, the R2 is proportional to many factors, actually 4 by 3 pi R cube times eta by kBt. If you end up looking at the Stokes equation of how a molecule would end up moving against a viscous force, the solvent will be giving a viscous force, correct? And if its viscosity is given by eta at a given temperature T, and the Rw is actually the radius of the molecule, if you assume the molecule is a sphere. This equation is written under the assumption the molecule that you're looking at is at an average spherical. Okay, it's just an assumption to just give an idea how the R2 changes. You can always have other models and still predict R2 from them, but this is a model that I think can be most easily related by all of us, so therefore I'm taking this. Radius of molecule, and the W includes with, I think, single monolayer of water. So if you assume that the molecule and its first shell is made of water, and if you assume it's a sphere, then the R2 is proportional, if you're able to see, to the size of the molecule. As the size of the molecule increases, R2 increases. If R2 increases, line width, which is R2 by pi, also increases. Meaning that as you go larger and larger sized molecules, the resonances will become broader and broader. So far, we have been taking an example of ethanol where lines are sharp. Soon, we would want to understand how does a protein NMR spectrum look. At that point, you will quickly realize that resonances are much broader. So basically, as you start increasing the molecular size, the number of protons increase. So therefore, the number of chemical shifts, or within a given space of chemical shift, many protons will come. So the line width increases, the number of protons increase, making it difficult to understand larger molecules using one-dimensional NMR spectroscopy. So the R2 has also additional effects that come due to viscosity and temperature. So if you are in a more viscous medium, the lines are broader. And if you are at a lower temperature, the lines are broader. Okay, so therefore, the whole point of detailing all this is that if you change temperature, viscosity also changes in turn, because viscosity is dependent on temperature. As temperature increases, what happens to viscosity? Increases or decreases? Sorry? Decreases. Yeah, as you increase temperature, viscosity decreases. So what you're able to realize is that the function of temperature is a little more complicated, meaning that as you increase temperature, viscosity reduces and therefore R2 reduces. So many people would like to do NMR at slightly elevated temperatures, not to increase its sensitivity by population difference, but by reducing R2. Did that make sense? Whenever you have a peak, the integral below the peak is a constant. Whenever you have a peak, it has a certain R2 by pi. Therefore, if the integral is constant, the intensity is dependent on the R2 parameter. So as the R2 becomes lesser and lesser, the peak intensity will go higher and higher. The signal to noise is always measured as the peak maxima and the mean of noise. So therefore, as you start going larger and larger molecules, there are times where people tend to play with viscosity and temperature by increasing the temperature, which reduces viscosity, and the denominator also increases, resulting in shorter T2s. I mean, longer T2s and shorter R2s. So whenever you have a resonance, the full width at half maxima is R2 by pi. And each resonance, the integral, the area under the curve, is dependent upon the m0 that you have. Area depends upon multiple parameters. If you really have to assume this to be a triangle just for the heck of it, you realize that if you increase one of the parameters, some other parameter has to come to keep the area constant. If the line width increases, the intensity drops. If the intensity drops, the signal to noise ratio is always measured from the intensity maximum to the noise that is being present. So if R2 increases, signal drops, so sensitivity drops. In order to improve the sensitivity, quite often what people do is to increase the temperature a little bit. What do I mean by that? Instead of working at 25 degrees Celsius, they might want to work at 37 degrees Celsius to improve the R2 characteristics. For some class of proteins called membrane proteins, people have to use additional co-solvents, which increases the size of the molecule a lot more. So people tend to work around 45 degrees Celsius in order to do something like this. The idea of understanding equations is to drive a point that over a period, if you're having an impediment, you'll be able to know how to handle it so as to get the maximum sensitivity. So now the viscosity changes could also come due to solvent changes between H2O and D2O. So remember that. Go find out which has higher viscosity, D2 or H2O, and why not. And the viscosity would in turn depend upon hydrogen bonding ability, and check whether a D2O can form stronger hydrogen bonds within the solvent, or, you're talking about hydrogen bonds across solvent and the solute. Solute here is the biomolecule. If the solvent can form hydrogen bonds within itself, then its ability to form hydrogen bonds with the solute reduces. So go figure out how do things change. And therefore that will end up affecting the viscosity depending upon how much D2O you have to use. And you all know, I just showed you in the last week that you have to use a deuterated solvent to do field frequency locking, in which case you cannot evade using D2O when you're using H2O samples. Some amount of D2O has to be there. So that does play a very small role. Let's recapitulate what we did. We were looking at how does a pulse program look at the spectrometer. If this is a one pulse experiment where an FID is acquired for an acquisition time AQ, for a given D1, we were looking at signals that arise from different NMR experiments. So far, we saw ethanol in D2O. This is what we saw yesterday. Dwell time will be given by acquisition time divided by total number of points by 2, where this is real points, where TD is total number of points, real and imaginary, real plus imaginary. And then we were also trying to say dt is 1 over spectral width. So that implies spectral width is number of points over 2 times acquisition time. Is that right? So basically, I just used these two dependencies and ended up relating them, where spectral width is given by the number of points divided by 2 times the total acquisition time. And we were trying to say the acquisition time is more or less set as 3 times T2. And then that's partly the reason why I started the discussion by trying to say, how does T2 or R2 change? As you increase the size of the molecule, the T2 reduces. If the T2 reduces, acquisition time reduces. If the acquisition time reduces, resolution reduces. So let's go back to the spectrum that we were trying to look at. So what do you see here is an FID for a carbon NMR. And let's go back, is that if I end up expanding, you see the triplet. The triplet corresponds to the proton. Correct? What he wants to know is that we spoke about the satellites, and he saw the satellites. Do you guys see the satellite peaks existing? Right? So the 2 triplets that are there on either side of it are the satellite peaks. Why are they coming? Let's measure the proton-carbon coupling that we take here. So here, it comes up to 125 Hertz. This is a very typical one-bond proton-carbon scalar coupling. Okay? Yeah? So we have been talking about satellite peaks. Why do satellite peaks come up? Because you still have 1% natural abundance of carbon where the proton gets split by this. You can always decouple carbon here, but that's kind of unnecessary. Okay? Yeah, so this is one point that we read in this thing. So why should we only believe one peak? Let's take a look at the quartet also. Do you see? Quartet also has a nice set of satellite peaks. There are times, and therefore, if satellite peaks can only come due to carbon, the hydroxyl peak should not have a satellite. Is that right? Okay, you might ask what these are. I'll come to it later. They are not satellites, which I'll tell later. But overall, you do not see a satellite peak for the H2O, the hydroxyl proton. Okay, did that make sense? Yeah? Okay, good. So now that being done, You won't see such satellite peaks for carbon because remember, you're already measuring at 1% natural abundance of carbon. If you acquire long enough, you might see some examples of it, but they are so less in intensity that we may never be able to pick up what's going on. Right? Two carbons that are labeled next to each other should be a doublet. So maybe there's something coming up, but there's so much into noise that we can't interpret. Yeah. And what did we see yesterday? We did see the spectrum and the points that are acquired in the FID, which when you Fourier transform, you end up getting the frequency domain spectrum. And the details that we wanted to see are, if you type show PP, it shows the pulse program that was used. And this is the first channel, the F1 channel. This is the F2 channel. There are two channels that are used, proton and carbon. The carbon is a direct detect channel, which is where you're applying the 90-degree pulse and you're acquiring the signal. And the proton channel is where you're decoupling to make sure the proton-carbon coupling does not evolve when you are acquiring the carbon signal. Why do we do this? Because you know that carbon, if you have a CH3, the carbon will split into a quartet, which reduces sensitivity, which is not good. So therefore, you don't want to worry about whether CH3 or CH2. You want to make sure all come up as singlets. Make sense? Okay, good. So let's ask some of the parameters that were set. Let's go to the spectrum first. If you see the spectrum, in the x-axis here, you see the spectral width. When I'm moving the cursor, you'll also be able to see on the top left, somewhere here, what is the chemical shift that I'm trying to show. So if I take it to the extreme here, you're able to see the chemical shift. The minimum chemical shift that you could measure given the spectral width here is about minus 17.8, maybe minus 18 ppm. Okay? I'm not able to move the cursor all to the left. So maybe it goes to minus 18 ppm as you're able to see, right? And the maximum chemical shift that you can measure from this is about 218.2 ppm, 218.4 ppm. Yeah, so that is the spectral width that you're trying to look for. So if you type SW, you'll be able to get the command on what is the ppm that is used to get the given spectral width. So it is about 236 ppm. Instead of asking this question in ppm, you can ask the spectrometer, what is the frequency in hertz? So if you type SWH, it comes up as 29761. Let's see. So 29761.9. So how many? By 236.63. So actually this was acquired in a 500 megahertz instrument, right? So basically what did I do right now? Let me repeat. You ask the spectral width in ppm. If you just type SW, it comes up in ppm, which is 236.63. Ask the same question in SWH, which stands for spectral width in hertz, you get 29761. So you take 29761 divided by 236.63, you get the frequency of carbon in megahertz. So in order to get it in proton, I multiplied it with 3.98, then you end up getting 500.5, which says it's a 500 megahertz in spectrum. Okay, so now that being done, we can also ask the other parameters. If you hit D1, you'll be able to figure out what is the interscan delay. The interscan delay is set to 2 seconds. And the acquisition time AQ is set to 1.1 seconds. So basically, you have a total relaxation delay of 3.1 seconds here. So if you ask the number of points, which is TD, total number of points is 64K, 65,536. So this is nothing but 64K points. So let's do that. 64 times 1024. 1 kilo in many of the computer language is not 1000, it's 1024. So 64 times 1024 is 65536, which is 65,536 points, indicates 64K points in the time domain that you have acquired. That means you have 32K real points and 32K imaginary points, right? So once again, let's ask if your acquisition time is 1.1 seconds, and if you have 32K points, what is the duration between points is our question. So I'm asking it in microseconds. So this will be 33.56 microseconds. So let's go to the FID. And then let's see whether between two data points, that is the duration that you have. Remember, this is going to show more data points than required, largely because it has both real and imaginary. So show data points, say apply, close. So if you check the difference between, what do you get there? 33.69. I'm sorry, it's not visible for most of the people. Basically, it says 33.7 microseconds. And that's exactly what we had calculated, 33.6 microseconds. Right? Of course, I'm not carefully measuring it. If I carefully measure it, it will be 33.56. Did that make sense? So basically, we are looking across various parameters, the NMR instrument, how you set up an experiment, the number of points that are acquired. As we said, the FID is not a continuous signal, it's digitized. Why am I taking difference between leaving one point in the middle? Because half of the points are imaginary, half are real. We will understand why half are imaginary later on, although you do see it on the point. So don't worry about it. So basically, the dwell time is determined by the spectral width. Therefore, if you set a certain spectral width, depending upon where you want to acquire, you already end up getting a certain dwell time. Makes sense? And importantly, if you guys are able to see the spectrum, let's also take a look at noise. How does it look? Oh, this ended up getting faced in a certainly slightly different way. You can always face it back. So you say EFP, and then you say adjust phase, and you can always adjust the phase to make it look absorptive. You can always get the dispersive by applying a 90-degree phase correction like this, but we don't have to do that. We like absorptive lines. So there you go. The most important aspect here is to realize that you have quite a bit of noise. This is what we mean by noise. If you end up taking the average, the noise would still go to zero, indicating that it's just stochastic. At an average, it's not existing. But at any given point of time, you have some randomness that is present with it. Randomness being, you will never be able to see anything periodic with respect to this. So therefore, if you keep repeating your experiments, noise will be random enough where when you add, they won't grow. On the other hand, signal will nicely grow only wherever there is a frequency. So this will keep on growing, correct? So therefore, if you do signal averaging, you can improve your sensitivity of the experiment. Does that make sense? This is what we saw yesterday as the signal to noise ratio. Okay, with that being done, let's take the next example where we did acquire the same ethanol. Instead of in D2O solvent, we ended up measuring the same in DMSO solvent. What is the difference between DMSO and D2O? D2O has the potential to give hydrogen bonds and take hydrogen bonds, while DMSO, for people who might not know, the structure is CH3SO CH3, where the SO, the O will be electronegative enough to accept hydrogen bonds, but there are no hydrogen bond donors, right? So therefore, this will slightly change the way ethanol would end up behaving, but let's see what we get. Yet again, you see the triplet for the methyl group. Let me expand the spectrum. So here is where you have the triplet, which is for the methyl group. Then let's see what we got here. This is the resonance for the solvent, meaning that you have DMSO D6, but you cannot always deuterate to 100%. You'll have still some residual proton being there. So this is a signal that arises from DMSO D5. Since that proton will now be coupled to 2 deuterium, 2 Ni plus 1, 2 times 2 times 1 plus 1, because deuterium spin is 1, you will have a quintet, which is what you see here. 1, 2, 3, 4, and 5. And just for the sake of understanding, you will also be able to measure the scalar coupling between them. I think it will come somewhere at 2.85 hertz, 2 hertz. About 1.9 hertz is the scalar coupling between the deuterium and proton in the DMSO. So that's a solvent peak. Let me zoom in here. And what do you see here is a little more complicated. You expected a quartet, but now that quartet is further splitting into something else. Do you guys see that? The resonance that's being present here is from the residual water that's present in DMSO. Unfortunately, deuterated solvents are hygroscopic in nature, so they start absorbing water from atmosphere, not from moisture. So if your solvent is not very clear, you will see D2O, H2O peaks that are being present, and that's what is coming here. So this is some contamination. But here, if you are able to see, this is the methylene proton. Previously, you expect the methylene proton to be a quartet. Now it's further splitting into something. Why is this happening? Can anybody explain? A quartet for the methylene protons. Now the quartet seems to be splitting further into a doublet. Why is this happening, and why did it not happen before? What is the structure of ethanol? CH3, CH2OH. Why does a quartet come? Because there's a metal group. So if it's further splits into a doublet, why should the doublet be split? Yeah. The OH coupling that didn't exist in water, because in water, there is exchange of the CH3, CH2OH, the OH to OD. OD-OH keeps on exchanging, and this process happens in a time scale which broadens the signal beyond the detection of the triplet. So you see a much broader line where the line width is more than the scalar coupling. So the line itself is so broad that you don't see it. So let us see in this case whether the hydroxyl proton comes up as a triplet. There you go. You slowly start to see the triplet for the hydroxyl proton as well, right? So let us see whether whatever we are trying to claim is indeed true. I want people to make a note of some of the scalar couplings that we are measuring. So let's try to take the methyl scalar coupling first. So you go from peak maximum, just one moment, yeah. Peak maximum to peak maximum. Somebody make a note, it's 7 Hertz. So the methyl protons have a scalar coupling of 7 Hertz. So now let's zoom into the methylene protons. The way to measure scalar coupling here is to a maximum to a maximum. And what do you measure for the methylene proton? I'm not sure whether it's visible. That's also 6.95, which is basically 7 Hertz. Okay, I'm measuring the maxima to a maxima. Be careful when you measure scalar coupling. You can always measure it within a certain range. For instance, you can measure it from this peak to this peak. That will also be 7 Hertz. This is what we learned in the AMX type system. You can measure it from, I'm sorry about this. You can always measure it from here to here. So NMR gives you multiple redundant measurements so as to give you a better idea of what is accuracy and precision. The same measurement can be done several times within one measurement, indicating that you can get a scalar coupling with average and a standard deviation, right? You can see that? So that's the 7 Hertz. So then we can try to ask, what is the smaller magnitude of coupling, which you will measure between these two peaks? And what do you end up measuring? I'm sorry, it's very feeble. It's about 4 Hertz. So the methyl proton had 7, methylene had 7 and 4. So therefore the 4 Hertz should belong to the hydroxyl proton coupling. Let's see whether that is indeed true. These are really measured data. These are not simulated. These are experimentally measured data. So you go to peak maxima to peak maxima. It comes a little higher because I'm not choosing the peak maxima correctly. So you have to choose one. There you go. About 4.3. I'm not measuring the peak maxima correctly, largely because I'm not able to pick up the maxima because of the larger shoulders. Okay. But overall, what you are able to see is that nicely the methylene proton coupling to the hydroxyl and to the methyl is nicely seen from the doublet of the quartet splitting that you see here, right? The magnitudes help you, so does the fine structure splitting. What is fine structure splitting? Quartet is fine structure splitting. The quartet splitting further into a doublet is a fine structure splitting. So what does NMR give you? It gives you quite a number of parameters. And if you pay close attention yet again, if the D1 of the experiment is carefully set, you are able to see the proton is integrated to 1, the methylene proton is integrated to about 2.06, and the methyl proton is integrated to about 3.06. That is a little bit of 3% error or even 2% error that's existing. That's largely because the hydroxyl proton has an error. Even here, the hydroxyl proton will exchange a little bit with the residual water, resulting in the error. If I did this to be 2, let's do that actually. Let's do integrals. Let's delete these integrals and reintegrate. You will see that very clear. The 2:3 will be okay, but the hydroxyl proton is the one that's causing error. Delete and then go to the spectrum. And let's say analyze, integrate, and let's pick an integral.
Can we estimate the amount?
And then if you end up. So what you guys are able to see here, if I re-reference the integrals with respect to the methylene proton as 1, then you nicely get 1.50 for the methyl protons, which is correct. 1 is to 1.5 is 2 is to 3, right? It's less than a % error, which why do we care about? But on the other hand, if the methylene protons are set at 1, the hydroxyl should come around at 0.5. You see, it's slightly less than 0.5. That's happening because the proton ends up exchanging with water. What's your question?
Can we estimate how much water is present?
You can estimate by integrating it. And assuming you know how much of ethanol is there, you should be able to estimate how much water is there. Totally. Right? Definitely is feasible. But if you take a look at it, the only problem is what will you refer it against? You can't end up taking the residual DMSO to integrate it. You need a reference. That's the problem with NMR. You always can relatively quantitate within a sample. Absolute quantitation across different molecules is not very straightforward. It can be done. You have to put an external reference for it.
Something of fixed amount.
For instance, let's take formate. Formate will give NMR signal at 10 ppm. The HCOH, the H in the HCOH will give 10 ppm. You have to put a reference that does not interfere with your molecule and comes well resolved, so that you can integrate that reliably, right? For instance, here also when I integrated, I carefully integrated such that this didn't come. Did you see that? So one has to be very careful, largely because if you also want to integrate the satellite peaks, which are here and here, which should be integrated, you're losing 1% of the peaks here. I didn't wantedly integrate the satellite peaks because that will lead to water also. So somehow I had to delete water and do this, this will become difficult. So I ensured by zooming in that my quantitation is reasonable only when I left the satellite peaks out. In theory, you should include the satellite peaks. I excluded them out because for the other one, unfortunately, water is interfering. Makes sense? So integral has to be carefully done. Only when you carefully set up the experiment and carefully do the integration, you'll get some quantitation within this system. If you didn't set up the experiment, this quantitation is gone. Set up the experiment properly and didn't do the integration properly, you'll get something wrong. Assuming you do all this properly within the molecule, you can semi-quantitate. Quantitating across ethanol and water within this might be a little tricky. Right? Assuming there's good resolution, you don't have overlaps and all that. Right? So NMR is semi-quantitative technique. It's not fully quantitative. So one thing that we are able to learn, the same molecule that you ended up measuring, why don't we try to overlay the spectrum that was acquired for ethanol in DMSO and in D2O. So this is the overlay that's being done. And there are some subtle differences you see. The methyl proton is slightly shifted. You see that in water, it's right around 1.08 or 09 ppm. But in the case of DMSO, it's 1.07 ppm, about 0.01 ppm shift. And if you take a look at the methylene proton, we have to take the middle here. That's about 3.56 ppm. While in the case of DMSO, it's 3.45 ppm. You see a significant difference. There's no point comparing the proton here because it's clearly difference between hydrogen bonded here with water, which comes at 4.7. This could be the water proton itself, because at the point that you have more H2O than ethanol, it's going to exchange all the ethanol protons. But anyway, the hydroxyl proton, it comes up here. This is very clear because if you think about the chemistry, you're talking about the hydrogen bonding ability of this guy with respect to D2O or HOD and DMSO. What is DMSO? Here, if you guys once again appreciate the fact, you have hydrogen bond accepting and hydrogen bond donation. On the other hand, here you have only hydrogen bond accepting capability. So what is this going to do with respect to the hydroxyl proton? It's going to take the hydroxyl proton, but do nothing to the oxygen. It can't do anything. On the other hand, for water kind of solvents, it can engage both of them, resulting in electronic environment that changes subtly in all these two carbons as well. So what you guys are able to see, NMR is so subtle that you just change the solvent, keep the same molecule. There are some small changes that come up. NMR is super sensitive technique this way. Chemical shifts get perturbed for a very, very small perturbation. We just changed the solvent. Ethanol didn't change. The bonds didn't change. Electronic cloud, if already it's electronegative, it will be taking the electrons from the methyl carbon. Now, if you're further taking it off, it's going to get further pushed. The small change in the electron cloud is enough for the chemical shifts to pick it up. Let's go back to the practical aspects, and the scalar coupling wouldn't change much. So let's try to measure it. What was the scalar coupling in the case of so that more or less remains same, 7 Hertz, and it remains 7 Hertz here as well. So things don't change much in terms of scalar coupling. Scalar coupling changes indicates dihedral angle changes. So here it's more electronic environment change more than the dihedral angle change. Does that make sense? You will see more of it as you go forward. I'm just giving you an idea how NMR data could be interpreted to understand how the molecule is behaving. And we took a simple molecule, ethanol, which is very well known for so many decades now, centuries actually, right? Taking a simple technique, making one measurement, how does things change? On the other hand, let's also ask whether the carbon NMR changed. Or do I have the carbon? Yeah. So let's say we take the carbon NMR. Okay, there you go. First question for all of you. Be prepared. Look at the major difference between carbon NMR acquired for ethanol. So the bottom blue trace is for carbon NMR for ethanol in DMSO D6. And the top trace is for carbon NMR for ethanol acquired in D2O. What is the first major difference you guys see?
Extra peak.
What is that extra peak? Very good. The DMSO has carbon, and the DMSO D6 will have the deuterium splitting of the carbon, and go check how many deuteria are you looking at, and therefore why does the coupling come this way. Okay, so that is one aspect. But overall, the effect that you saw for the proton chemical shift change is also clearly visible here. The methyl carbon is quite shifted, while the methylene carbon is less shifted. On the other hand, proton was opposite. The proton, the methyl proton were more shifted than the methylene, the methylene proton were more shifted than the methyl proton because they were directly attached to the hydroxyl. So all this put together gives you a complicated information of how the electronic environment changes upon any chemical changes that happen in your molecule.
So in the DMSO spectrum, the height of the peak of the methyl peak is much higher, which means that the width is much smaller. But if the width is smaller, then the R2 value is smaller.
Who wants to answer this question? It's a valid question. He says if he has to compare the methyl peak height, let's do that. Let's do that. Good question. He wants to compare the methyl peak height. The integrals work out. Is that correct? Okay, let's assume that's matched. Yeah, now I match the methyl peak height. Is that right? More or less. You agree? So the question that Google is asking, methyl peak height matched. Why does the methylene peak height be this different? Who would like to answer this? Therefore, you reduce sensitivity by half. Correct? Did you understand that? So you previously only had a quartet. The quartet split, then that height is going to half. Integral has to remain same, which it did, by the way. The other explanation is what you gave. The line widths are also more in this case, indicating there is some interesting relaxation that's happening between DMSO and DMSO and ethanol versus water and ethanol. So the R2 is changing, and the major reason why you went half is because of hydroxyl proton coupling. If you couple, you're going to go from 1, you go to 0.5 to 0.5. From 0.5 to 0.5, you go to 0.25 to 0.25. That's how the coupling goes. We saw that in an AMX system. Did you see that?
Yeah.
So same thing is happening here. So two things are happening. In addition to R2 changes, you're also able to see that the coupling is the major change. 50% change happens due to coupling. Make sense? Good question. Good. So now that being done, so let's take a molecule which is simple, but at the same time not too simple. So this is a molecule which you are able to see in the bottom left called cyclosporin. So this is a classic example where you have so many protons that are being present. You see how quickly the NMR gets complicated, right? This is still small molecule where the NMR is quite sharp. You still do get resonances that are well resolved. You see multiple doublets that are being present. Maybe these are doublets of doublets. These are not very easy to answer until you measure scalar coupling across and you see splitting here, and you see this is potentially a doublet of a doublet. If you see nicely, you're able to see a doublet of a doublet. So the NMR spectrum quickly gets complicated across many different spins that exist. Okay, so to interpret something like this, given the complexity of the structure, immediately makes you guys realize, oh God, just by proton, we can't do this. You guys agree with that? Just taking this NMR spectrum, giving you the structure, you cannot, we just saw ethanol where nicely triplet, doublet, integration, everything worked out. But now when you take something a little more complicated, quickly things get difficult. Remember, a protein is going to be much more bigger than this. That's what I was trying to say. When the molecular size increases, number of protons increases. Number of protons increases, NMR gets more complicated, right? So quite commonly, this is where other nuclei come to the rescue. So quickly, I'm introducing 2D NMR in a sheepish way. What I'm trying to show here is that, well, the proton NMR is really complicated, which you see as a red trace. If you end up doing a carbon proton resolution, so what do I mean by this? I'll take one nice example to exemplify this for you guys. Don't worry about the colors right now. Don't worry about what is blue, what is green. Are you guys able to see wherever I have drawn the trace? So if you guys see where I've drawn the line, you see one proton that's present there, but it's able to resolve multiple carbons, meaning that multiple protons are hidden below that resonance. There are many CHs which happen to have the proton chemical shift being identical, but their carbons being different. For instance, there are too many protons below this. Let me take another example to show this in case this doesn't make sense. Just one moment. Okay, for instance, let's take this part. Yeah, if you see in the proton NMR spectrum, there are many peaks here. You do not know what is a scalar coupling. It's a doublet or a triplet or a multiplet. It's very difficult to distinguish. How many protons are below this bunch of protons is very difficult to interpret. The moment you do a 2D experiment where each proton will not just report its chemical shift, it'll also report its directly bonded carbon's chemical shift, and you correlate them. It's like an X, Y kind of a plot. And immediately what happens? This bunch of mess, which has many protons, nicely resolves into 3 CH protons. There could be other protons that have NH which don't come here. This is a carbon to proton experiment, not just any nuclei. It's just carbon to proton. There could be an NH that's hidden below it, which we can't see. We can never see OH anyway, because O is always NMR inactive. So slowly what I'm trying to make you guys understand, I'm trying to bias you guys to accept the fact that we'll be moving away from one-dimensional NMR very quickly. Although the one-dimensional NMR experiment is super nice and interesting, we have to go to higher methods so as to extract as much information as possible for the given molecule.
Sir, one small question. If we use some non-polar solvent for that ethanol experiment, like don't we expect nothing to happen? Or
Excellent question. I'll show you. I had CDCl3 in it, but I'll show you the spectrum on Wednesday and we'll start there. I'll share the spectrum with you. That's a very good question. When you don't have an hydrogen bond donor or acceptor, what happens is your question, correct?
yes, sir.
It's very interesting. I'll share the data with you. You analyze it yourself. You are right. You are in the right direction to understand how to exploit NMR to get more information. Good job.
Yes.
Okay. We'll meet again Wednesday. Please prepare and come. Okay. Thank you very much. Bye-bye.